This is a demo I would set up in class. We would have water inside of 2 syringes. As you push water out of one, it must enter the other. The water is non-compressible, so as you push it down, the pressure will equalize throughout the whole system. This will make a different feeling of force that you would exert on the small one compared to the force on the big one. This is Pascal's principle. Let's explore it together. So today we're going to start with Pascal's principle. This concept is different from yesterday because we're going to be applying an external force, an external pressure to our fluid. And so when you apply an external force to our fluid, if our fluid is non-compressible, then that force will be transmitted through all of the particles. Thus, if you were to think about pushing down here, the reaction is that the water will come out all of these small holes. And so the pressure that happens inside of our bottle is uniformly distributed throughout the fluid. And thus the kind of evacuation speed throughout all of our holes in this example is equal. The idea of the pressure being equal inside of the container is called Pascal's principle. It'll also explain the workings behind this hydraulic lift. It also explains the differences in the syringes that we saw in the video. So here's what we were looking at in the video. We're looking at pushing on a big syringe and pushing on a little one. So as you move the little syringe in, right, you are changing you're doing work, I guess, on the system is the best way to put it. And as you push this one in, you're expressing force, I guess, exerting a force on these molecules. But since it's incompressible, those molecules exert force on the other molecules and continue to exert force through the whole container until the pressure is uniform. So we know that pressure is a force over an area. So if the pressure in each one of these systems is uniform, that means that the force to area ratio is uniform, which means that the force on each side does not have to be the same. So as you see, pushing the small syringe will only take 10 newtons to make a force over area ratio that produces the pressure. Over here on this side, with a larger area to make that same pressure, we need a larger force because of our larger area. That's what's happening in the syringe. So this is about pressure being equal in the container. Getting that pressure is about doing work. That's another step. Work. Work will get us the pressure, and pressure being uniform inside our container is called Pascal's principle. This is the principle behind a hydraulic lift. So the concept that through a small area with a smaller force, you can produce enough pressure inside our container that on the other side, the ratio of force to area, if the area is big, the force can be big, and we can lift something quite large, like a car. So in this exact example here, we're going to inspect a 14,500 Newton car. We're going to raise it with a hydraulic lift. We have the radius of the small piston over here, and the radius of the big piston. We want to find the force that must be exerted on the small piston to lift the car. So what we're going to do is we're just going to set up some pressure balance between the right and left sides. So the pressure on our right side is going to be pressure equals the force 2, side 2, over area 2. Which is going to equal the pressure in the whole container and equal the pressure on the other side, force 1 over area 1. Of course, we know enough numbers to plug these in, so F2 is the weight of the car divided by the area. Area is the area of this circular piston, so we're going to do pi r squared, where they give us the radius of the large piston. We're going to set that equal to the force required on the other side over the area of the other side, pi, and then our radius squared. Okay, so that we can solve for force, and we're going to get 803. And I actually have this up in a simulation over here that I'm going to pull onto this side. Here's what we're expecting to see. And if you look at our simulation, they give us the weight of the car, which I put in. I had to scale up our radius, but that's okay. I scaled it up on each side, so it won't affect our final answer. So I scaled up our radius of our car side and the radius of our pushing side. So notice that we do have to push with this 803 Newton force. Now, if we push with a force on our fluid, we'll be able to move the car some certain distance. So this is us being able to hold the car up. But if we actually want to move the car, we can move the car with this certain ratio. So let's watch this function here. So as we push down this left side, we need to push it for a really long time to rise the car on the right side. Now, there's a couple reasons for this. Right? On the bottom, they show you F times D. That should make you think work done. Right? Now, it's going to take work to move this fluid because you have force and distance, but also you have volume conservation. Right? You are minimizing the amount of volume on the left side and pushing it onto the right side. So that has to go somewhere. But on the right side, that area is so much larger, right? Look here. This is such a bigger area. So to get that same amount of volume, we're going to have different heights that we need to move our two pistons, just as shown here. So we can pick up with where we left off on the simulation and talking about the moving of the different distances. The first thing we can do is say that the volume of water on the first side must be the same as the volume of the water on the second side. The next thing you consider is, what is this volume? Well, it's a distance that we push. So for example, D2 times A2. So instead of writing volume 2, we could write A2 D2. And then on our left side, we could express the volume on that left side as A1 D1. And these must be the same. Now, if you take this concept and multiply by something else that's the same, the pressure, right? Pressure. Then right here, we've actually simplified to something quite interesting, pressure times area. From our definition of pressure above, we realized that that's actually force. So pressure times A1 is F1, D1. And then pressure times area on this side is F2 times D2. And once you write it out like that, you realize that what you said is the work in on the left is the same as the work out. Oh, ain't that obvious when you think about it? Energy in is energy out. So this is Pascal's principle and how it applies to hydraulic lifts. Hope you enjoyed.